All right, there we go. Welcome to the last day. My name is Melissa Osborne. I'm also with the events team. Thank you for joining us on the last day. I want to introduce Joey Mart and Jennifer Lee from also with ServiceNow. Let's give them a round of applause. Start the morning.
Whatever.
All right, I'd like to ask you please to take the moment to mute your cell phones, any mobile devices that you might have with you, your laptops, anything else, to give them the respect for the next 15 minutes that they gave this presentation for you guys. For 40 minutes, they're going to give a presentation. For the following 10, then I'm going to run around with the mic and do any Q&A. So if you have any questions, just raise your hand and I'll run around with the mic to make sure that we can hear you. This is a really echoey room, so I'm just going to make sure that you guys really talk pretty loudly when we do the Q&A. If you have any questions or need anything, just exit the same way that you guys came in. But go ahead and just, here we go. Thank you.
All right. Hello, everyone. I'm Jennifer Lee, and this is Joey Mart, and we both work in platform team and works in platform persistence. So we're going through, the kind of explain how we run our operation inside our ServiceNow Cloud. So first of all.
So I'm Joey, eater of ribs, Chihuahua owner, Model 3 driver, new Chicago resident, apparently. So Jennifer and I both worked mostly in the San Diego office together, where most of the platform engineering happens. We tend to get involved in a lot of the bigger customer escalations. We tend to deal with a lot of the scaling and growing and trying to plan for not only like immediacy of customers that have an urgent need for some performance improvement, but also to be looking forward 5-10 years into the future to figure out how we can continue to scale our product to accommodate customers whose data is growing, to accommodate new customers who have totally new, diverse ways of doing things. And while we're thinking about this stuff, we're also working in the persistence layer, which is basically the bottom of the barrel. It doesn't get any lower than persistence. So we deal a lot with databases. We deal a lot with the operations teams that handle deploying instances, managing instances. So you can imagine a more traditional web application that would be hosted on something like AWS or on Azure or Azure. I've heard it pronounced both ways. Somebody correct me if you work for Microsoft and you know what the real one is. Azure. Now we know. Those tools have more sort of commodity, elastic growth and compaction stuff. We, managing our own data centers, have to sort of handle that stuff ourselves. So I'm now getting into the intro stuff, which we'll talk in a couple of slides.
All right.
So
I'm Jennifer, and I've been with ServiceNow for more than 6 years. So I've been started with integration team and then working with web APIs, and then I started core platform, handle with scripting engines, and then started going down lower and lower layer, and now I'm at persistence layer. So persistence basically offers the data access API to all our upper layers, so we're the foundations of the whole ServiceNow platform. And like Joey mentioned, we actually handle a lot of the customer onboarding, so especially you are a pretty sizable enterprise and you want to get into ServiceNow, we do handle cases where we have to pre-planning and get our operations ready. So with that said, I think we can...
That's us, so...
Yeah. So in this session, we will go through talking more about how we run our cloud, what's the general architectures, and how do we scale your instance up or down, right? We are also elastic. We're slightly different than most of the cloud-based services, but we also are elastic. And then the third point you will take away is how do we handle normally performance issues?
So like sort of the high level here of what to kind of expect from coming here and spending the next 50 minutes, hour with us is we hope that you can leave with having a better sense of how we run things, how we run our own data centers, but more importantly, why we run our own data centers, why we run in a single tenant architecture, which is a common point of contention. And I think most importantly, the difference between tuning for performance, improving performance on your instances through like more precise targeted tuning, and scaling, where you're scaling out to accommodate increased user base, increased traffic, that sort of thing.
So when you start, on your mobile device and your laptops, when you connect to ServiceNow, for example, hi.servicenow.com, what does that really mean? When you start https.hi.servicenow.com, you actually start a transaction with ServiceNow Cloud. And that really means that you started to connect to, one of our data centers. And we have, how many of those?
A lot.
20, 10?
So the dots here are major data centers. So you can probably see, depending on your instance, most people probably don't actually know where their data is located unless it's a particular concern. But you see a dot there in San Jose, one up. That one north of Washington actually is Vancouver, right?
Yeah. So these are actually dots for our production instances. We also have more data center that runs our internal or developer or testing lab instances.
The secret data centers.
Yeah, that which I'm not allowed to show. So when you onboard as a customer, you get to pick which location you want to host your instance. And instances are generally paired, so for high availability. So you don't get to pick. You want to have one in North America and one in Australia. So they are generally in regional, and we already paired them. And if you're European company, generally will give you EMEA location, and then if you're American company, will give you 2 locations, East and West in North America.
So to clarify that too, like when we say we pair, so we'll kind of go over what the data center pairs actually mean to availability and to just general delivery of service. You can choose sort of a pair, but the pairs are pairs. So one example is San Jose and IAD, which is Virginia. That's one of our more common pairs for instances in the Americas. So if you have a high availability instance, which you do if it's production, you'll have data in San Jose and in Virginia. And if for some reason you wanted to be in EMEA, you'd have to have paired in London and Amsterdam, for instance, would be the other kind of pair.
So we drilled into, for example, North America, you may be on our standard setup. Actually, this is pretty typical. One is in SJC, San Jose, and one is in Virginia, IAD. And so between the two, your instance is actually hosting on both sides, and there are high availability connections between those. That's pretty much. So inside both the paired data center, your instance, like I just mentioned, actually existing in both sides. So if you look at the darker shade of instances, they are like active sites. And if you look at the gray, it's actually your passive sites. So between those two, we have bin log replication. So your data active site is the one that actually serves the current transactions. When your user actually connect to ServiceNow, they will be redirected to one of your active nodes in the active sites. And then all the changes from there is going to replicate to passive sites. And so our paired data center doesn't really say the whole data center on one side is passive. So for each of the instances, you may be on IAD this week, and then some other company may be on SJC this week, and then next week they may have changed.
So there's a lot going on this slide. So as the coming slides, we're going to basically zoom into the different components, what they mean. This is sort of high-level visualization of what a pair of data centers would look like. So when you're looking at this, let's say you work for Acme Corp, you have acme.servicenow.com, you're going to be a pair of these blue rectangle things. So imagine you're the one on the far left. The darker colored one would be your primary database and nodes. You'd be paired with nodes in a database in the standby data center. with like we're kind of showing with the more dimly colored blue box. So each one of these blue boxes is essentially an instance. And so to kind of drive the point home too, we use the term instance a lot, and it really is kind of an abstract term. So as a customer, you pay a subscription, and you really just get a URL. And the instance is the general thing that's represented by that URL. But it can be comprised of multiple JVMs, databases. We have all kinds of things like gateways and read-replicas that we're going to explain, and that makes up the greater instance. So we're going to zoom in, and you can be thinking of this in terms of this is your company's instance, this is your stuff.
Right. It's like Joey mentioned, each instance really, we have a one domain name. So you have a hi.servicenow.com, to us, that's an instance. And you have another one, acme.servicenow.com, that's a separate instance. So we zoom in to one side of the data center, you'll see actually each company or even a enterprise could own multiple instances. Internally for ServiceNow, we run multiple instances for different functions, like Hi is our customer-facing functions, and also how we handle all the incidents or the problems through Hi. Even internally, we build our features and we report back to Hi. That's our instance for our development cycles as well. And we run a separate instance which called Build Tools 1. And internally, we put all our test results and Jenkins results all into a separate instance. And those are actually two different URLs, that's actually two different instances. And between your instance and one instance to another instance, the data doesn't really, doesn't collide with another. They store in a separate database. So the benefit of, instead of like different cloud service companies, they offer multi-tenant architecture. Our key difference is that we are multi-instance architecture. Multi-instance architecture, the benefit that gives you is that it's data isolated, so your data is never going to get mixed with other customers' data. Even inside your company, multi-department, if you run different instances, your data doesn't collide with the other departments' data. Another benefit.
So the thing to be thinking about too with data isolation. So if you picture physically, so there's a distinction between what we're talking about here sort of as logical components that make up an instance and actual physical stuff. There's a big building that's a data center. Data center has cages of racks of servers pumping megawatts of power that really are the physical components that make up all of our instances. So while you might have a physical server that has, say, so we'll separate servers into like a database server, application server. We might have multiple instances of MySQL on a database server, but you literally have your own MySQL executable, your own MySQL instance that belongs to your company's instance. So there will be acme.servicenow.com as an instance. We'll have a database named Acme. It has its own MySQL process running only that Acme database, I guess.
Yeah. And your file directory is completely separated. So.
And then logically, that sort of the data isolation occurs. You're not necessarily having your own physical server, but we logically isolate things into separate stuff.
And that gives you also the advantage of that is that you can control your instance. You decide when you want to upgrade. So many instances in our farm runs slightly variation of different versions. We try to bring them like at least the latest two major versions, but within those you decide when you can patch it, when you want to upgrade, when you want to do major upgrade. That's a lot of flexibility actually to you. And we also get a lot of visibility of what your instance is running and how you want to control your instance. You can change the parameter, you can decide whether or not you want to encrypt the database as what we just offered this release. And then many other features, you have your own decision.
And the really cool thing about how we have why we like our single tenant architecture. So if you think about the diversity of all of our customers, like you're walking around here and you're seeing different company names that you recognize on badges, different industries. So you might have a company like Macy's, which might be very busy, say the day after Thanksgiving or during a 4th of July sale. Then you might have a company like an insurance company that mostly is kind of dead over holidays. Both of those companies have very different desires around when they want to maybe take downtime, or when they might want to accept the risk of upgrading or deploying some new product. So by not imposing upon our customers some prescribed timeline where we'd have to say, well, we're deploying London, so we're upgrading London Memorial Day weekend. I hope that's okay with you. We might have some customers that would be excited, and other ones that wouldn't be so happy with us. So being able to kind of control based on your own needs, having a single tenant architecture, you won't be affected. Macy's won't be affected by an insurance company upgrading or resizing their MySQL database over Memorial Day weekend.
It's a very good point. So now we drilled into more detail into what is inside a single instance. The smallest instance when you started, you have at least 2 nodes. And we're only looking at one side again because we start zooming in. And when your user connect to it, you're going to go through our load balancer. Each of data center has at least a pair of load balancers to make sure that our load balancer is our gateway to enter ServiceNow Cloud. And once you connect to it, it will redirect your traffic to your instance, and that means one of your application nodes. So basic instance, you got 2 application nodes, and you have 1 primary database. Okay. So as your user increases, you might have more, and we can actually scale you up. We add more application nodes to serve the traffic. And you continue adding more users, your business is doing great. And we might give you bigger database because your data is increasing and your transaction volume is increasing. What your business needs is increasing. And so if you have even more users, you double the volume of it, we give you more nodes. That's in general how we scaled up our instance. And as your data volume increases, we don't really constrain you in a single database. We could start to add you to multiple databases. And that's in general, like as your traffic increases, we also increase our size as well.
So this is all like a really super cool animation. Like I hope that everyone kind of picked up on how rad this was. So basically, like we started with a basic instance that had, so the little black boxes within the greater blue box are JVMs, those are nodes. The primary database is that red cylinder. So we'll kind of go into detail later, but the database itself is everything. Your configuration lives in the database. Your data obviously lives in the database. The JVMs, the little black boxes, are just kind of dumb things that run code. They would be nothing without connecting to the database. So we're able to scale out, adding more JVMs to increase concurrency, and everything goes to the database. And in case, just as a quick aside, so we have the load balancer handles basically just round robin distributing transactions across the different JVMs. But that's the entry point. So when you hit acme.servicenow.com, you're hitting the load balancer, and it handles via magic determining which node to send you to.
So just to recap, that's, if you see the ... it's your users, increasing, and we also scale from application nodes. We can also scale from database nodes. And we think database is more important because we work on database end. So let's zoom into, look at each of the components. And application nodes, what do we mean by application nodes? I think we mentioned that earlier, but kind of quick. Application node really is a single JVM process. We run OpenJDK, and each of the Java process, that's basically how we run our platform. Our platform code is running on that Java process, and each node runs we embed application server, which is Apache Tomcat. We're going through many different version upgrades. We keep up to date with the current Tomcat, and that's the web app server that hosts your HTTP transactions. And each node, we do have already a database connection pool that already set up that persists. It's already there. So whenever the Java code needs to persist the data or read the data out, they use one of these 32 database connections.
So if you're like me, as soon as you start seeing numbers, you're going to start doing math and trying to see where you stand. You say, well, my instance has 2 nodes, and each node has 32 connections, but there are 1,000 people in the call center who are all connecting. That doesn't seem to add up. So the thing that's worth mentioning here is, so there's a distinction between a transaction as represented by a user performing some action, loading a form, clicking a button. That really is one round trip to the server, which is sort of a single transaction. But a single transaction typically will have hundreds of database transactions. So our application nodes and our database nodes are physically located, in the same rack essentially, with a super fast connection. So the latency between the JVM and the database is like basically nothing. So we have a bunch of lightning fast database transactions. For the most part, it's rare for a database transaction to take more than 100 milliseconds. And even 100 milliseconds is really slow.
Yeah, to us, 100 milliseconds should be considered a slow database transaction.
Right.
So when we mention about transaction, probably we use this terminology a lot. We actually separate from HTTP transaction versus the database transactions. One, like Joey mentioned, HTTP transaction could be more than one database transactions. And why is the 32 connections enough for a single application node? A single application node can host, many thousands of HTTP transactions. But whenever you use them, you could use them only for 100 milliseconds. When once you're done, we actually load the data back to the memory or the disk, and you freed up that transaction, you freed out that connection, and that connection can be used by another application threads. So we're going to talk about more within that, Java application. And inside that Java application, when you have thousands of transactions all out happen at once, so we do sort of doing a concurrency control. So you want to make sure, you have in correct load to your application. You also don't overwhelm the application nodes. And so we're using semaphore pool. Internally, we call them semaphore pool. It's actually how we implemented Java concept of semaphore pool. It's not directly using a Java library or it's not the OS level semaphore pool. It's our logical semaphore pool. We're using that to control how many concurrent HTTP transactions that application node can handle. And so out of the box, if you install it, you go to semaphore pool sys_semaphore table. They actually already define different semaphore pools that can take different type of HTTP transactions. So out of the box, you can see there's an integration pool, and there's a presence pool, there's a asynchronous message bus pool, and debug, and default. And most important ones is actually the default pool. Default pool means when the transaction comes in, when HTTP transaction comes in, based on your URL, we actually decide which pool this transaction belongs to. And so these two presence and message bus pools is actually we added in Geneva. They are only handling for user presence. Those little avatar you see in our instance, those are the presence. And presence has a special traffic pattern. And so we give them a separate semaphore pool to control so they don't overwhelm other transactions.
So tying this back to kind of the distinction between transactions too. So you have a user that clicks a button, loads an incident form, say. That's one transaction. That one transaction basically occupies a single semaphore for the duration of the transaction. While it's holding that semaphore, it is issuing multiple database transactions, and it's preventing other transactions that come in from other users from acquiring that semaphore. The thing that's worth mentioning here too, you can imagine if you're also like me and you like to have 100,000 tabs open to feel important, you could pretty easily take down a system if you just click a bunch of links, load a bunch of stuff, and eventually exhaust all the semaphores. So we also have the notion of a session synchronizer. So you, as a single user with a single session, can only do one thing at any given time, essentially. So if you're loading a long running homepage and you go to another tab and try to open an incident, you might see it sit there spinning. That's not necessarily because you don't have a semaphore. It's not necessarily because that page you're loading is itself slow. It's because you are being blocked because your session is already doing something.
Right.
So that is a gating mechanism before semaphore pools.
Right. And we used to have a case where one of our customer opened an incident that one of their users has sticky keyboard. So when they press enter, or they were constantly sending transactions over. So, but application node is not going to be down because of one user's keyboard is stuck, because then it's sending a lot of transactions. We actually have the session sync, like Joey said. It doesn't, so it will queue up the messages, but it's not going to overrun the whole application nodes. So talking more about how we handle semaphore pools, how we implement semaphore pools. Semaphore pools, each semaphore pools are individual message queues internally. So when you have a lot of HTTP transactions coming in, variations, based on your URL, we actually assign you to which queue that goes to. And then each queue, semaphore, when we say semaphore pool, there's a number earlier behind it. That really means how many processing threads that we allow each semaphore pool can have. So each gear here is an example of a transaction thread, processing threads. And so whenever you have a processing threads available, it's going to take the next available message. And when you have a really large amount of messages that overruns a single node for some odd reasons, we'll just overrun the queue, and once the queue is full, you actually just those messages gets rejected. So that protects at least the application nodes being up. It can still continue processing, but if there's anything that behave abnormally, then we don't take down your user transactions. We don't take down the whole nodes. So each node also has a scheduled workers list of 8 scheduled workers. These are also, with a parameter, you can change that, but by default, we do, size them, pretty evenly. We think that 8 scheduled workers for each node is the good size for us. And what does the scheduled worker do? Scheduled workers are background worker threads, and what they do is they handle, asynchronous jobs. So things like, schedule imports. You really don't have the user's UI transaction. You don't need the immediate feedback for those things. We use a schedule worker that just slowly pick up the job queue and process the asynchronous business rules, periodic reports, or periodic imports. They runs in the background, and we make sure that they also, a schedule worker is not going to overrun, take out the whole JVM resources. So at cases, you might have a very heavy imports. For example, if you're integrating with another enterprise systems, you may have a large imports periodically, or every day, or every week. In that case, that could use a lot of application node resource. In such case, we actually could do is we add a pair of dedicated worker nodes. What that means is that we actually tell our F5 load balancer, don't route any UI traffic in there, because these workers are going to use a lot of resource. When they use a lot of resource, your user UI response is going to be slow. So you don't want to impact any users, but you do want to continue processing these big jobs. So we could prescribe the dedicated worker nodes, and they would just sit there and then grinding through the heavy jobs. And these are commonly used by the integrations, and then.
And when we say commonly used by integrations, I would say that dedicated worker nodes are pretty uncommon. More often than not, they're not necessary. When we do have them, the reason is usually some very heavy integration traffic that's pretty consistent that we've detected to have contended with normal traffic, normal scheduled activity in a way that actually affects normal user traffic. And this is kind of an operations thing. This isn't the sort of thing that you'd want to go and say, oh, I want a dedicated worker node. This is the kind of thing that we have some pretty detailed metrics, and we pretty much know when we need it.
Mm-hmm. So as we just talked about all the mechanism we have, and as the workload increases, you got more users, you got more HTTP traffic, and more jobs. How do we continue to scale up? So like Joey just provided hints earlier, we capture a lot of stats for each of the application nodes. So in general, if you look at stats.do, I don't know if you guys do anything, take a look at stats.do or XML stats.do, we capture at least 200 to 300 different metrics every minute. But most importantly, that affects scale, because that gives you a lot of hints when we're seeing problems. Then we can look at throughout the times, and where is kind of peak hour starts, and where the traffic starts, where is the spike. That's helping us for troubleshooting. But among those, what's the most important ones for us to scale the instance is the CPU time. And so we collect them every minute, and we calculate a score based on CPU time every night.
So we get this stuff. We have a huge big data instance, basically, and we're throwing so much data at it. The instance itself generates the XML stats page, which you can see for your own instance. Just go to your instance URL /xmlstats.do if you're an admin. And there's a lot of detail. And if you know the magic flags to pass to it, you can get specific detail about, say, cache statistics, hit and miss statistics there. The default XML stats page includes JVM CPU, but we also have monitoring at the server level. That's literally capturing top, say, every minute. So we know for a particular JVM how much CPU it's occupying. We know for a JVM, that is on a shared physical server, how much it might or might not be exploiting resources compared to the other JVMs. So we have a lot of logic to handle not only adding nodes to an instance to accommodate increased CPU load as a result of increased concurrency, added users, and removing nodes when they're not necessary to be elastic, but we can also move nodes across physical servers. So you might have 10 nodes on your instance, another customer might have 10 nodes, you might share a few nodes, and we might find that those two instances are busier than some other nodes, some other instances, and we can move them off and basically balance CPU across customers so the physical resources are never going to be spiked in any one place. And we do this every night.
Right. Yes. And so when you actually every night, well, after we calculate the CPU score, when certain instances over certain threshold, we will decide you need to add more nodes. Like you have more traffic, you do have more workload, you need more nodes. So if that's the case, a change ticket will be filed, and we have to get your agreement with, and we'll add 2 more nodes. Every time when we do a change, we add pair. So pair of nodes will be added, and then also, if you don't use that much traffic, everything's quiet for many weeks, and you don't have that much users for certain times, then we actually could remove some of the nodes too. So now we're talking about database. So the most important piece in this picture. Primary database we run, used to be we run on MySQL. Now we actually moving slowly. Our data centers all started to migrate to MariaDB. Some of you might already know that because we've also filed change tickets when we migrate. And those, I think we're almost there, probably 70% penetration of MariaDB now. But next few quarters we'll continue moving more. And we are running with InnoDB storage engine. Each instance, again, you own your own database, so you can, we file a change ticket, you decide when the migration should happen or can't happen, and we declare maintenance windows for that. And what's interesting is in this whole picture, database is actually our central communication points between our application nodes too. So if you notice that the picture doesn't really have the dots between the application node to application node because we don't have anything, node doesn't directly talk to another node through any HTTP or any special protocol. The way between the nodes, if they need to communicate between each other, for example, if you change something, you need a cache flush. The mechanism we're doing is going through database. We actually, behind the scene, we insert a cache flush records, and every node is actually heavily polling to see if I need to do a cache flush. So most of the communication, if you need to sync in the whole cluster, all that communication point is in the database. And database size is determined by the buffer pool size and the disk size. So buffer pools. So I'll let Joey to explain what buffer pool
So
is.
Basically, when you're dealing with MySQL, when you're dealing with any relational database, you want it to be lightning fast, and you don't want to be impeded by having to go to disk. Going to disk is slow, going to memory is fast. So we want to have as much of the database as possible in memory. It doesn't make sense to have a database that has enough memory to fit, say, every attachment or every log entry or every audit file. We don't care about that stuff. We want all the stuff that people are actually accessing, the data that queries are normally hitting, to be in memory at basically all times. So we have a capacity algorithm that we use to determine what the appropriate database size is based on the actual storage footprint of some key tables. So the three common ones are just sysuser, task, and CMDB being the most common core tables in our product. We want those three tables to fit in memory at any given time. And so we size according to that. And this is something that we calculate nightly. If we see that there's a case where a database is undersized based on that storage footprint, we're going to file a change and increase the size to accommodate it. And this is unlike JVMs where we can kind of move things around because JVMs are dumb. This is something that you'd actually know about as a customer. You have a change request, you would schedule it, and it would be sort of similar to doing like an HA failover, essentially, where you're going to a new database that's been spun up with all your data.
And one note to say, well, demo instance and developer instances do have your upper limits. So if you own a demo instance, we're not going to let users to be able to create unlimited CMDB records or task records. Then you automatically size up to take up a giant server. So putting things in perspective, and what does that really mean? Because I think we got a lot of questions from customers like, can you host 10 million records? What does 10 million, can you really run 20 million records? So these are a few examples we have in the farm. 40 million task records really is 270 gig on the disk. And so, but the total, because we use database so much, the total disk size is actually 8.8 terabytes to run an instance like that. So if you're thinking about how big your task size is, there are rooms. And also, another instance we have, their CMDB records is over 300 million records. And that really, in terms of disk size, is 2.3 terabytes. And the total database size mostly is in the CMDB. They don't really use other tables much, so others are relatively small. They don't have large attachments. So the total disk size of the whole database is 5.5 terabytes. So just to kind of give you a perspective of how big the size is, what that really means.
So we can probably get through these next three slides pretty quick. These are just some of the ways we handle scaling at the database level. So there are basically two things. So Read-Replicas, gateways. And again, these are things that we determine the need for at an operations level based on the traffic that we observe and based on the performance metrics that we capture. Read-Replica is just an exact copy of your database that sits right next to your database, and we distribute load. So it's configurable to know which queries actually go to the replica. Being that it's a replica, there is some sort of accepted latency, essentially. So you might have the read replica be a few seconds behind the primary database, but for doing things like homepage reports, that's generally acceptable. But if your instance is one that's determined to need a read replica, it's configurable to say, I want homepages, reports, whatever, here's my acceptable latency, all that stuff's configurable from within the instance if a read replica is something that the metrics suggest is important.
Right.
And then gateways, unlike read replicas, it's not an exact clone. A gateway is we take data out of the primary database and put it in a separate physical database. Being that it's two separate physical databases, we can't move tables that have relationships. So we can only move table groups like attachment, like audit, like log, things that are usually pretty big, take them out of the overall primary database for the overall health of the primary database. And then we just handle routing database queries to the gateway as needed.
Okay, so just give an overall example of how our large, instance setup. So the few, probably top 10% our customers are pretty large, and these are pretty typical setup, like 60 application nodes, and one primary database. Primary database is still our most important piece, where we can't scale up primary database. But database does scale horizontally as well, so we can add, as the traffic increase, load increase, we add more replicas, read-replicas to redirect the heavy queries, or we can continue adding more and more gateways to move the big size tables aside so that they don't overrun the primary database. So how do we actually, when we scaled up, what's the procedures we're going through? And like we said earlier, you have a passive side on one side of the continent, the other side is your active side. And so when you actually connect, all the nodes on both sides will connect to the primary side, active side databases. And so you see all the transactions, actually, the connections actually directly linked to the left-hand side, which is the active side. And right-hand side, yeah, that's the right-hand side. The right-hand side is dotted line where F5 doesn't direct HTTP traffic to it. That's our right-hand side. And then for those, you do have also database that continuously replicates. That's our standby databases. And these we can size up without interrupting services, right? So we can size up, if we need to size up, we size up the primary, we size up the read-replica, we size up the gateways. And then once they're ready, it's ready to switch all the nodes. The nodes can then all go to primary, the passive side database. That's kind of we do HA transfer, and so using that as part of our day-to-day size, procedures, and then we can redirect all the traffic over to the other side. And then by the time we finish routing everything to the bigger size database, now we can resize the other side, which is now the passive side. And so we're doing this kind of operations thousands times a week. So it's not like when you're running data center operations, you have disaster recovery. Disaster recovery drill doesn't get run, maybe runs twice a week. So when you need them, the high availability, you notice that, oh, your drill has problems, doesn't work. We actually incorporate that into our day-to-day operations. So we run tons of HA transfers. So in case there's anything happens, we just do that all the time. So we're gonna repeat that. So the next part, we're gonna talk about how do we troubleshoot performance. So the difference between performance and scalability. And performance in general is, we define as the response time of your HTTP transactions, your UI transactions. And scalability really is how can you handle more concurrently without decreasing the response time. If you're thinking about analogy where you can, thinking about moving cars, driving a truckload of stuff from point A to point B, you can think about that. Performance is how fast you can get from point A to point B, and scalability is how we can provide you more resources in order to get there, faster, to improve your performance, maybe. And in some cases, performance, more resources does help. So in this case, traffic's really high. We add more lanes. It's gonna help you to, reduce the traffic, and you can get from point A to point B faster. And that's where every night we run automation scoring so that you don't ever get to this situation. But there are also times when just adding lanes or adding resources doesn't really help you. If your traffic, your transaction, your message is big truck, adding more lanes is not gonna get that truck go faster. And most of the performance problem that we're seeing is, people driving on the road and suddenly they have trucks take over the road. And so, for example, you have a slow query for some reason. You have, users issuing slow query, run a large report that queries a large amount of data, but they don't really use much. They just, dump most of the result away and use only one of them. Or you have a, very heavy business rules, heavy ACLs. So it depends on external, transactions. For example, if you click on UI actions that end up triggering external integration, and you have to wait for that response in order for that UI transaction to finish. Or you get to the point where you have cases where it's a big truck of load. So it's a really heavy stuff that you have to process, and that's one single transaction. So report, integration, you end up using integration that impacts your front-end UI, and then, or very heavy imports. Another example is the homepage. So this is like a role train. So you have a homepage that have multiple reports. Each report is also very heavy. And so that's one of the symptoms we've seen in the field. And on the other hand, we also have cases like this. Every car is a Ferrari that drive very fast. However, they're in a parade. They drive together. So your page doesn't do anything until all the cars arrive and they have to kind of form a certain formation. So like we say, session sync earlier, if you do have a single page that issues a lot of asynchronous transactions, asynchronous transactions, your page doesn't do anything until all your transactions is finished. But so each of the transactions fast, but they don't really do anything until all of them is done. So the common solutions we provide these kind of thing are, we provide scaling so that you don't run into a traffic jam. And we actually have a monitoring on SQL statements. We capture all the slow queries. And we move all the heavy processings to get them into a single lane so that they don't overrun the whole highway, or just completely give them a dedicated worker node so that they don't even be on the road. And so our goal, internally, to keep the road pretty clear, running smoothly, and so with
driving on the wrong side of the road, apparently.
There's that. So that's pretty much what we have. So hopefully you get kind of a good understanding of how we run our cloud, how do we scale up or down, and how do we generally handle performance versus scalability problems.
And I should also say, we did go over because we're a couple of Uber nerds, and apparently talking about database scalability is not something I'm capable to be verbose with. So we don't really have too much time for questions, but I'm happy to stick around after and talk to anyone outside if someone wants to chat or has questions or anything. I'm free, but I think we have 4 minutes for questions.
Yeah.
We can push it a little bit. Okay, so if anyone has any questions, feel free to raise your hand and we'll chat.
Hi. So doing a worker node and UI node separation, what are the reasons for not doing for that?
Reasons for what?
For not doing that, not to have the separate worker node. So what advantage it brings in if we don't separate it out, the way it comes out of the box, and what we lose if we separate them out?
You're talking scheduled worker activity?
Worker node and the integration node and the UI node.
Oh, like a dedicated worker node. Oh, okay. Well, I don't know. What do you have?
The dedicated worker nodes?
So what's the cost? What do you lose by moving something into a dedicated
What do we lose? Because there is a reason why we do for it. Otherwise, we don't separate them out. So when we separate them out, is there anything we lost?
Not really. I mean, you're really just, that's at the application node level. So it's still dealing with the same database. If there's data that other application nodes need, it's still in the database. So really, the only thing that you're gaining there, that's like the metaphor with the train. You're taking something that uses a lot of resources that get in the way of normal user activity. And so you're just getting it out of the way. But you don't really lose anything. It's actually kind of a big net gain. It's a resource cost to have additional dedicated CPU that users don't actually get to use, which we generally don't like, but
okay.
Is that?
The other one which I have is that the gateway database edition. So I heard you said that there is no joins across the tables. If you are pushing your attachment, especially I'm concerned about, not to the logs. And if I have to programmatically do a join, or internally when I pull out the attachment from my form, then how that is going to work?
Well, it's actually a separate query in that case. So it's only joins that we have single database queries that would have to join to accommodate bringing back the data we want. So the case there would be like CMDB and task. So you have a task that has a reference to a configuration item. You want to query for all tasks that point to a particular configuration item. We have to do a join to do that in a performant way. But with attachments, it's usually single record. Same with audit. I'm looking at a form. I want all the audit records for that record. We don't really issue queries that say, give me all the audit records for some general query. Same with audit and attachment, I would say. Yeah.
Okay, thank you.
Can you hit it right? There you go. Thanks. To you and then to
And then to Redshirt.
So you talked about a lot of things, how they're laid out behind the scenes. What I want to know is for a customer trying to see why things are not right on their instance, is there some way, some visibility into what exactly is going on behind the scenes to see the bottlenecks?
We do have, if you go to ServiceNow Performance homepage, for each of the instance, we do locally collect a lot of stats, and we do show that stats in our own homepage as well. But we also
about the graphs.
Yeah, the performance graphs. You actually can see that. You can also go to slow query. We also collect them in slow query tables that throughout the times we collect what are the biggest query you run or how many fast queries but runs a lot of times. So there are tables that collect all that.
And we have the aggregated stats too, not just for queries, but general. We have slow transactions and slow scripts as of, I think, before Jakarta. And we aggregate it pretty well. So we, like Jennifer said, we have like average runtime, and you can see things that run too much. And that's usually the starting point to see what performance is as it's perceived by users, which is really what we should be caring about, what you should be caring about. We care about performance across resources. And so you can see things like CPU of a particular JVM, and you can see if you had, say, a spike at a particular time, you can see memory usage of your JVM. The goal really is that you shouldn't have to care about that. It's something that you can see. Ideally, that's something that we will already be responding to and trying to address, if not as there's a specific anomaly that's transaction-driven performance problems, or it's generally like, well, this instance is performing as we expect it to, and it just uses resources. We have to scale under the hood to make it work.
Right. If you look at syslog transaction table, that's for each of the UI transaction, we'll collect all that stats. So we also have a summarize of how much time you spend on business rules, how much time you spend on SQL, how much time you spend on
network,
ACL or network, and so how much client browser rendering time, because sometimes when it's slow, it's not necessarily backend slow. The browser could take forever, like we mentioned about a lot of AJAX. So browser is basically waiting. So we have all that stats in the syslog transactions too.
One more quick thing. So sometimes the system hoses, you have like a session get stuck, like you talked about one of the scenarios with the semaphore being locked in. Is there any way to kill that? I mean, even if you try to do it on the client, it doesn't really kill it on the server.
We have transaction quotas that should automatically kill that stuff. That's the goal, is we define quotas for particular transaction types. So after a certain amount of time, the system kills them. And that should be the
you got to wait
stuff
for that.
like that. Yeah.
Right. Thank you.
There's actually a way to kill a transaction. I can't remember the name of it, but your instance name / I can't remember what the command is, but you can kill your current transaction.
Cancel my transaction. Yeah, that's like the little thing that pops up if it's taking too long.
Right, you can cancel your own. Most of the cases that really gets to the problem is we cannot cancel them, and they really get to the point in the code that they get stuck. They don't get signals that can send out to throw exceptions to actually terminate that transaction. And that's really something we have to, if we see that becomes potentially a code fix we have to do. But in general, you can kill them.
Redshirt.
Hey, my question, switching gears a little. I'm curious, what are the monitoring tools used within your infrastructure, and what are the scripting tools you use to do all the behind-the-scenes changes that you talked about here?
We're actually using Java code to collect a lot of our internal stats, like the cache managers or memory size. JVM does offer quite a bit of the APIs that we can call. We directly call them from Java code. And we do run, I think the JRobin graph I was mentioning about the performance graph, we use a script that runs periodically to present them, but actual collection of the data is run in the Java code.
What are you using for your scripting language or languages?
JavaScript. I've seen the scripts include.
Okay.
We use our product a lot, actually, to manage we have an instance that manages deployment, orchestration, all this stuff. The same instance that does your instance clone, handles deploying new instances, resizing, and it's all running using our own orchestration tool, our own workflow.
That was the answer I was hoping you'd give.
Okay, yeah.
Okay. So I guess our time's up. So can we do one more? Okay.
And then anyone else can kind of run to the front of the room and for the next.
Yeah, and yeah, we can leave the room and I'll talk outside.
For high availability, why is it an active-passive setup and not active-active?
Good question. A big part of it is just data integrity is part of it, I'd say. I mean, we don't want to have to manage writing to multiple locations and then managing concurrency across different things. So we have the single point of failure, ultimately, as the single database. And in general, our application isn't really write heavy. It's very read heavy. So 75–80% of queries are usually just reads. And so distributing load across read replicas has been the way to manage scaling out the database. And we haven't really ever seen cases where having an active replication actually helped us in most cases. But we do have a lab team that is working on all the new crazy ideas. We test things out, and if we see benefit, it's something we consider. But yeah, for now, that's not something that we really
Yeah, that generally
get
makes
into.
our architecture a lot simpler if we don't have both sides of database changing. Especially passive nodes, we're still collecting a lot of local information, so that gets writes to the database as well. So we don't want to end up having two different databases. And if active, master replication doesn't quite work, then we have to deal with two different databases to merge the data.